Okay, good. So this is this part three is about learning stochastic problems, in particular monotone stochastic problems. So let's maybe start by a quick recap. So this is what we define a stochastic optimization problem as in this context. So we have a stochastic problem, you have some constraints, you have some objective function you want to maximize, minimize. The main thing that changes in stochastic optimization is that your inputs are now changed by random variables. And for simplicity, we will always assume these random variables are independent. So you have n independent random variables drawn from like classically known distributions. Data-driven stochastic optimization is precisely what happens if these distributions are not known and you only have some kind of sample or historical data. And we will always assume that the function is between 0 to 1. You can also work with settings where like it's between 0 to h, like some other parameter, like the guarantees that we'll prove will accordingly scale linearly. And as you're saying, like the objective is to maximize or minimize the expected value of the function. Some of the examples we saw, like simplest was the revenue maximization. Maybe the example we talked was like we're trying to sell a carrot to a bunny, how much to charge the bunny. When the bunny is like each day a new bunny shows up and like from some underlying distribution, and you want to maximize this. And this is just not just a toy example. I mean, it generalizes to very broad applications in auction design. We talked about optimal stopping problem. This was very similar to like the profit inequality problem that Paul has been talking about. This generalizes to something called online resource allocation. We'll discuss more about online resource allocation tomorrow. Pandora's box generalizes to a bunch of stochastic probing problems, Gittin's index, and so on. There are like lots of other problems as well. So Paul talked about stochastic Steiner tree, for instance, like an example. But you can talk about many, many stochastic problems in many, many fields. And the main question we want to ask is like, okay, what if the distributions are unknown? Can we come up with some general techniques to learn such stochastic problems, learn a good algorithm for such stochastic problem? And when I say algorithm here, algorithm basically means some kind of parameters of your algorithm. For instance, in revenue maximization, it might be the price that you are offering to the bunny. Optimal stopping problem, it might be like some thresholds you are setting, when to stop, when to accept the next random variable. Good. So the main question was, what's the minimum number of samples T that are needed, IID samples, so that your so-called regret is at most epsilon, which is f of opt minus f of alg. And again, to clarify what I mean by samples here. So the samples here, these are n-dimensional vectors. So one sample is an n-dimensional vector, where the ith coordinate is basically the value of the ith random variable. Good. So the tth sample, small tth sample, is basically an n-dimensional vector. And because these distributions are not identical, these are arbitrary distributions. So in some sense, you kind of need, at least naively, in the full feedback so-called setting, you need full samples. Good. And one thing that we defined formally was this notion of TV distance, which is very useful, especially for analysis. Given any two distributions over usually some common support, it's kind of the best kind of pairing you can come up between these two distributions so that the outcomes are most likely the same. So for any two distributions, it's the best possible. Formally, it's called coupling, like the math technical term is coupling, but basically it's some kind of a pairing between the two distributions, such that if this happens in this world, I'm going to simulate the following thing, this other thing in the other world, and such that individually, locally, they look the same, but together they are more likely to be the same, equal. So that's TV distance. And some results that we saw, first was the so-called simple Chernoff union bound, was the case where the number of algorithms is small. In that case, basically just by applying Chernoff bound on every individual algorithm, you argue that on your number of samples, the empirical average is basically very close to the true average. Take a union bound over all possible algorithms. So you'll get some guarantees which is logarithmic in the size of the algorithm. So this guarantee is reasonable. Some downsides, one of the biggest downside that we were not happy about was the fact that it's usually not polytime, in the sense of the number of algorithms is potentially exponentially. And then empirical risk minimization is something that we don't know how to do for exponentially many algorithms. Because for many of these stochastic problems, when I say that I know how to solve it, so by the way, like when I'm trying to do some data-driven aspect of a stochastic optimization problem, of course, the first question is, even if I had told you the distributions upfront, can you solve it? If you don't even know how to solve it for known distributions, it's hopeless to solve it for unknown distributions. So that's why we have first assumed that I can solve the stochastic problem for known distributions, but I've not assumed that I can solve it for arbitrary distributions. I've assumed I can solve it for these product or independent distributions. So empirical risk minimization, I cannot do it in general. So the other approach that we discussed was like when the distributions are discrete, you can use this technique via TV distance to argue that actually here you can still design a good algorithm. So what we showed formally is that if the support size of each distribution is at most k, you can first learn each individual distribution, but just by taking its empirical average to within a very small TV distance, and then construct a product distribution from that and feed that to your stochastic optimization oracle to come up with an algorithm. Maybe to illustrate this a little bit more, let me just mention one example. So let's say n is 2, like you just have two random variables, some d1 and d2. My samples would look like some tuples, like maybe like 0.5, comma 0.1, 0.3, comma 0.7, a bunch of such tuples I get. Now the thing I want to clarify is the way I'm constructing the distribution. So there are two ways of now defining a distribution D, two natural ways from your empirical samples. One is I'm going to uniformly at random choose one of these tuples, and then I'm going to output that pair. That's like one way of naturally defining an empirical distribution, is that you choose one of the pairs at random. These were your samples. And then I'm going to just give you that pair. That's, first of all, not even a product distribution. So instead, when I write something like this, these hats, the way I'm going to do it is different. I'm going to first draw one of the pair, like one of the samples at random, and just look at the first coordinate. Then I'm going to again draw one of the samples at random and just look at the second coordinate. So that's what I want to clarify, that when I'm giving this to my offline like stochastic optimization oracle, I'm giving this so-called product empirical distribution. It's not a uniform distribution over my samples, because a uniform distribution over the samples would naively mean that I'm drawing like one of the samples and then I'm giving you that entire tuple together. Whereas I'm doing like, actually, I'm just going to draw like the first coordinate first separately, then I'm going to draw a second coordinate uniformly at random sample separately. So that's how I'm going to construct this so-called, sometimes it's called the product empirical distribution. And now it's a product distribution, so I can feed it. So separate, first we argue that this each individual coordinate, at least for discrete support, it has a very small TV distance. It's like very close to the actual distribution. And separately, then you argue that even if you take this product empirical distribution, it's also very close to the true distribution up to this factor n. That's why like I've scaled down epsilon to epsilon over n if I eventually want the TV distance in d and d hat to be epsilon. Does this make sense? And like, again, I'm not getting into too much into the details of the kind that you can actually improve this n squared to n by something called as Hellinger distance. The reason turns out that if you just sum up the TV distances, that's usually a bit weaker. It's kind of like applying union bound naively. So you can do something better because it's a product distribution. So I'll not get into those details, but you can shave off this factor, n squared to n, and that's known to be tight in general. Okay, so any quick questions from, like, this is more like the recap part before we start for today. Okay, good. So the plan for this lecture is actually how to handle continuous distributions. So the last result that I just talked about, the distributions were discrete. So in discrete distributions, you could actually learn each individual distribution, each ith distribution within very small TV distance. But now once you have continuous distribution, this will not be possible. So the reason we care about continuous distribution is, first of all, like many problems don't admit discretization. So many of some auction design problems and many other problems, you can show that if you kind of constraints cannot be satisfied once you discretize. The other thing is that even if you can discretize, usually if you try to feed it into the result from the last slide, like the last slide, the uh, okay, I guess I'm missing a k here. It's nk over epsilon squared. Uh, so k was the support size. So if you try to apply results from the last slide, basically what I'm saying is discretization. You can't discretize very finely because otherwise you'll get like very suboptimal guarantees. And if you don't discretize finely, then the guarantees are anyways incorrect. So discretization doesn't work in general. So, and what are the main challenges for continuous distribution? Like to apply the approach from the last slide, is that the most important thing is even if I give you a distribution over like just a scalar distribution, not a high dimensional distribution between 0 to 1, and I give you a bunch of samples from a continuous distribution, you cannot hope to learn it in a small TV distance. So the reason is the following, it's a continuous distribution. So imagine there are no point masses. So every point has like the density is tending to zero in some sense. So you cannot even like you get a bunch of samples because it's a continuous distribution. All those samples that you've seen, like in some sense, their probability is zero. There's no way you can learn even the support of the distribution. Hence, you cannot, like after your sample, there's no way you can tell me like a coupling such that, or like there does not even exist a coupling. And this is like formal. The intuition is precisely this, that for a continuous distribution, it's impossible to learn the distribution so accurately, like such that 99% chance you're going to exactly output from the same distribution. Like that's what TV distance learning means, because in some sense, even the support is impossible to learn for a continuous distribution. Any particular output has chance zero. Good. So that's the one challenge. And okay, the fact that you cannot learn a distribution exactly means that you cannot even hope to design like a data-driven stochastic optimization algorithm for arbitrary algorithm design problem. Because in some sense, you cannot hope to learn the distribution exactly. You can only learn it up to some approximation for an appropriate notion of approximation we'll define later. And then we have to somehow, at best, what we can do is like you can learn some distribution, try to use our offline like stochastic optimization oracle to solve it, and then run it. But I mean, in general, if you change the distribution, the behavior of your algorithm could change arbitrarily. If I define like an arbitrary stochastic optimization problem, then as soon as you change the input slightly, like maybe the output was initially 1, and as soon as you change some input slightly, it becomes 0. Like the behavior could change arbitrarily. So you cannot hope to solve arbitrary problems. So that's why I need like the algorithmic problem to be somewhat well behaved. And as what we'll talk about, like we'll talk about monotone problems, stochastic monotone problems, roughly, which basically means is if I kind of increase the distribution, the value of the optimum increases. So questions like an algorithmic problems of this kind. A priori, like if you change distribution, things could arbitrarily go bad. So that's the plan. Okay, let's make it a bit more formal. Uh, and also like another remark is like for all these stochastic problems, we usually cannot apply standard black box online learning algorithms because usually like those results assume like Lipschitzness or convexity and so on. And for general like optimization problems, our functions are much more complicated. So they don't satisfy these assumptions like Lipschitzness and convexity and so on. Good. So first, let's look at the first challenge, which was the fact that I was saying that if you have a continuous distribution, it's impossible to learn it in small TV distance. So, I mean, one might ask a priori, am I immediately doomed or is there any hope at all? Is there anything I can do? So if you have a continuous distribution, even let's say just like a single distribution, scalar distribution, like taking values between 0 to 1, what can I learn? And so some of you might have already heard like the so-called DKW inequality or so on. Even if you have not, like the point is that although you cannot learn your original distributions, so this figure is slightly off. Like imagine the support is from 0 to 1, not like from -3 to +3, but you have some CDF of your distribution. Although you cannot learn it exactly, the continuous distribution, you can learn some band around it so that you can argue with very high probability the CDF is within some kind of a band or envelope, you may call it. More formally, like what you can show is that the so-called DKW inequality, it basically says that original distribution has some CDF capital F of X. I can learn after roughly like 1 over epsilon squared samples, some F hat X, such that for every X, they are within additive epsilon from each other. Okay, like a very crucial aspect of this inequality is it's saying this guarantee holds simultaneously for all x in your support. It's not saying like a weaker bound would have been take any particular x, fixed x, let's say x equals 0.5. The chance that your random variable is below 0.5, you can learn it up to an additive epsilon. So I'm not claiming just that it holds for a particular value of x. I'm saying it holds simultaneously for all values of x. And it's a continuous distribution, so one might even wonder, like it's in some sense infinitely possible values of x. It holds for all of them simultaneously. Is the statement making sense? Yeah.
This was some arbitrary high probability, right?
Yeah, so it's with probability this 1 minus delta. So this delta, I guess I did not comment. Yeah. Yeah. So that's why you have a log 1 over delta floating around. Good. And yeah, as you might wonder, like, I mean, okay, the first time you see something like this, it sounds crazy that, okay, like you have infinite support. How am I going to take the union bound and so on? It seems impossible. But okay, once you've seen this sufficiently many times, it's not that crazy. Like usually, like whenever you have infinite support, it's like things like if you've seen VC dimension, it has connections to that, or you can maybe discretize the support. And so like, okay, here's a simple proof. Slightly weaker bound, like I'm going to lose an extra log 1 over epsilon factor here. Let's say I don't care about like extra log 1 over epsilon factor. So let's say t is greater than log 1 over epsilon times 1 over epsilon squared. Then what I can do is basically I'll just discretize and take a union bound over all of them. The crucial aspect is I'm not going to discretize in the x space because, yeah, so we have to discretize in the quantile space. So there are some points where, like on the y-axis in some sense, like I'm looking at multiples here of multiples of epsilon instead of multiples of epsilon on the x-axis. And then basically just apply the union bound, like concentration inequality, Chernoff bounds, followed by union bound. The point is here now you have to take a union bound, not over infinitely many of choices, but only like 1 over epsilon choices. So that will lose you this log 1 over epsilon. But otherwise, things are all good. You can also shave off this log 1 over epsilon by more careful analysis or via like general machinery such as VC dimension. So it has the same, it's connected to the fact that like VC dimension of intervals is like a constant. So that's the reason. These are all like related concepts. Good. Okay. But even if the details were not clear, like the takeaway message is, even if you have a continuous distribution, there's some hope. I cannot hope to learn the distribution in a small TV distance, but I can hope to learn this distribution in this additive CDF approximation. The question now is like, is this approximation good enough for us, for our stochastic problem? Like if I learn each individual distribution within this approximation, can I do something about our stochastic problem, or for what class of stochastic problems does this suffice? Any question? Okay, good. So as you're saying, like there are two challenges to our like learning stochastic problems for continuous distribution. One is how to learn a continuous distribution. The second challenge is, even if I learn in some approximation, how does it translate to our any guarantee for my stochastic problem? So now let's look at the second challenge. What do I mean by these so-called well-behaved problems? I need some kind of a control on the behavior of my problem. Like if I change the input distribution slightly, how does the performance of my algorithm change? So the class of problems we are looking at right now are the so-called monotone stochastic problems. Roughly, it means the following, that if I feed into my stochastic problem a larger distribution, so I'm going to formalize what larger distribution means in a second. But if I give you a larger distribution, the value of your algorithm should only increase. The converse is also fine, like monotonically decreasing problems, stochastic problems are also fine. Like if you give a larger distribution, the value only decreases as long as like it's going only in one direction, either like increasing or decreasing. So informally, if this is clear, like now let me formalize this. What does it mean by a larger distribution? So here's something, again, a concept that's, very good to know if you've not seen it before. So even for like one-dimensional distribution, standard scalar distribution, you say like one distribution, like di hat, stochastically dominates another distribution di if it has higher tails, in the sense that for every threshold, probability that x hat sorry, it should have been xi hat is greater than equal to t is greater than equal to probability that xi is greater than equal to t. So in some sense, for every threshold, the higher random variable, the chance that its value is more than the threshold is only greater than the chance that the lower random variable, di in this case, xi, has value above this threshold. Is this making sense? Yeah.
But only for thresholds in between 0 and 1?
So I'm assuming my distributions have support 0 to 1 in general, but yeah, you're correct. You can, in general, it's defined for every point in X, but I'm assuming my distributions are only between 0 and 1. So is this definition clear? Yeah. So it's just saying that, yeah, in some way, like intuitively, it's just saying that, yeah, one distribution is more likely to be always higher. Good. And like in a higher dimensional, I'll define like a product distribution, d hat, to be larger than this if each individual components are higher. So if as long as each individual di hat is like greater than or equal to di, yeah. So this is like a partial order. It's not a total order between distributions. But yeah. So it's a very nice concept. It has very, very connections to many, many other things. Good. So now now I've defined this so-called stochastic majorization or an order. And roughly, as I was saying, like, what do I mean when I say my problem is monotone? I basically mean that if I give you a distribution which stochastically dominates another distribution, f of optimum only increases. Okay, there's some subtlety here as well. So there are two definitions. One is the one that I'm just defining. This is the so-called weak monotonicity. So what that says is, if you have d hat, which dominates d, then f of opt hat on d hat. So look at the optimum for d hat, run it on d hat. That value is greater than or equal to f of opt is of d. So whatever is the optimum for d, you run its value. So this is the definition that I guess I was saying before, that as you increase the distribution, the optimum only increases. Does this make sense? And turns out like all our problems, like revenue maximization, like if you kind of have like a different bunny who values things only higher, you can argue that, okay, the revenue only increases. And that's very often true for most stochastic problems, like the optimal shopping problem, Pandora's box, all of these problems. You can show that if you replace the original distribution by something higher, optimum only increases. The reason I'm calling it weak monotonicity is that actually the result we'll prove does not, at least the result we'll prove today, does not hold for weak monotonicity. It requires something a bit stronger. That's why it's called strong monotonicity. It says again that if I give you two distributions, d hat and d, where d hat is larger than d, then it says f of opt of d hat, okay, is greater than f of opt of d. So the right-hand side is the same. So you have the smaller distribution. It has some optimum opt. Its performance here. The left-hand side is slightly different. It's saying that I've changed opt hat with opt. So I'm saying that look at the optimum algorithm for distribution d. I'm running that same algorithm on a higher distribution. The performance of that algorithm should. Whereas here I was saying I'm looking at the optimum algorithm for d hat. Its performance is increasing. Here I'm saying look at the optimum of this lower distribution. Whatever that opt is, I'm going to run that on d hat. That performance should also increase. Does that make sense? Yeah, so it's like some slightly subtle difference, but there is a difference, and there are stochastic problems which satisfy one definition and not the other. Question? Yeah.
Would it make a difference if we said it has to be dominating on, like, not just opt, but on any solution, or would it be too strong of a section?
Yeah, so that's a great question. So I think maybe I have a remark as well. Yeah.
Okay.
So this definition is true. I'm saying only for the optimum here. An even stronger definition, let me call it like super strong monotonicity, would have said something like this is true for every algorithm. For every algorithm, potential algorithm, if you change the distribution from d to d hat, like a larger distribution, the value of your algorithm increases. That's in some sense, let me call it super strong monotonicity. So there are three levels in some sense. Weak monotonicity just says the optimum increases. strong monotonicity says just for the optimum here, and super strong is what the third one we are seeing. So there are examples like, so for instance, the revenue maximization problem that we talked about, like bunny selling, that even satisfies the super strong monotonicity. But for some of the, say, Meyerson's mechanism, which is like when you have n buyers trying to buy a single item, turns out that satisfies strong monotonicity, but not the super strong monotonicity. So that's why there are like, yeah, different stochastic problems fall in different classes. But yeah, as you were saying, like strong monotonicity does imply weak monotonicity. In that sense, it's fine. But yeah, so these are different hierarchies. And ideally, we want to design algorithmic techniques that apply to larger and larger class of stochastic problems. Yeah. Does this make sense? So this is strong monotonicity. It does apply to still like most of the problems that we saw, like optimal shopping, even like revenue maximization, Pandora's box, and yeah. Good. Okay. So the main result I want to talk about is about this result due to Guo, Huang, Tang, and Zhang from Colt and Stock. It basically says that for any strongly monotone problem, you have roughly n over epsilon squared samples suffice to learn an epsilon optimal policy. Is the statement clear? So, and their algorithm is also like pretty much the same as we saw before. The algorithm is just for each individual distribution, you have like these many samples, n over epsilon squared samples. For each distribution di, separately learn di hat, which I mean, I'm not going to do anything fancy. I'm just going to take the empirical distribution just for that ith random variable and apply the dkw inequality to argue that, okay, di hat is close to di. So learn this each distribution individually, construct this product empirical distribution, which is the product of these learned di hats, feed it to my offline like stochastic optimization oracle. Whatever algorithm I get, the claim is that this algorithm already is good. It gives you like epsilon, it's epsilon optimal. As long as your stochastic optimization problem is strongly monotone. Does it make sense? And the reason it's somewhat challenging to prove this result or like somewhat surprising is that you cannot hope to learn any of these individual distributions in small TV distance. As I was saying, that because these are continuous distributions, any single continuous distribution, you cannot hope to learn in small TV distance. Because I mean, if you could learn a distribution in TV distance, then in some sense you're already done, because 99% of the times, like your learned distribution is basically the same as the actual distribution. So in some sense, that's why things are kind of obviously done up to like 1% error. And values are bounded between 0 to 1. So 1% error is like just 1, like 0.01 in some sense error. Good. Sorry. So again, so although we cannot hope to show that we can learn this in a small TV distance, the proof approach is also very interesting. The approach is of the following kind. You have some original distribution D. Applying something like the dkw inequality, we are going to construct two envelopes for this distribution. An upper envelope, which I'm calling D plus, and a lower envelope, D minus, such that the original distribution D lies between these two envelopes, the plus and the minus. And these envelopes are very close to the true distributions, like the TV distance between D and D hat, D plus is at most epsilon, D and D minus is also at most epsilon. So it's like very close. We can also separately argue that our learned distribution D hat, the one that we constructed here by taking the product of the learned individual distributions, that distribution also lies between these upper and lower envelopes. So both D hat and the true distribution lie between these two envelopes. Turns out this will suffice. Like both these things simultaneously holding will suffice to argue that the value of our learned algorithm on the actual distribution is at least like whatever is the true optimum minus some 2 epsilon. Okay, so again, I want to highlight the fact that we've learned here some D hat d hat is between d plus and d minus. What's funny is we never learned d plus or d minus. In fact, it's impossible to learn d plus and d minus. Like the upper and the lower envelopes are impossible to learn. We've only learned d hat. Which in other words, what I'm trying to say is we need to complete the proof. We just need to show existence of an upper and lower envelope. We don't need to actually compute them or learn them. Okay, maybe like to illustrate this, let me give a small exercise. So let's take a few, like maybe 2-3 minutes to solve it. So the question is the following. Come up with 3 distributions. I'm calling it d minus, d plus, and d hat. But let's say 3 arbitrary distributions on 0 to 1, such that the distance between the bottom and the largest one is at most epsilon. But the TV distance between from the middle one is very large, is like 1. So yeah, so maybe take like 2 minutes to think about the question. So it's 9:17 till 9:19 maybe. Yeah, so the question is, come up with some distributions such that just to an exercise to to digest the definitions better. It might be good to think about it for 2 minutes. Okay, does someone want to speak up? Anyone? Okay, maybe any volunteer? Okay. Otherwise, I mean, I'm happy to just give the answer. Yeah, maybe you're shy or okay. So okay, the example I had in mind is just the following. So imagine you have 2 distributions, d minus and d plus are the following. So d minus is 0 to 1 minus epsilon, like multiples of epsilon. It's say the uniform distribution. D plus is also pretty much the same, just that I'm going to replace 0 with 1. So d minus is like uniform 0 to 1 minus epsilon. D plus is being uniform from epsilon to epsilon 3 epsilon until like 1. So it's d plus clearly dominates d minus. The only difference is that 0 has been replaced with 1. So the TV distance between d minus and d plus is epsilon, because in some sense, most cases they are the same. You can easily define a coupling, like the ith thing goes to I epsilon goes to I epsilon, except I being like 0 or 1 over epsilon. But I can define a distribution which is in between the two. Let's say it's supported on like epsilon over 2, 3 epsilon over 2, 5 epsilon over 2, which is clearly in between the two in the sense of majorization. But the TV distance is very bad because it has like a totally disjoint support. This distribution in between. Hence, the TV distance is extremely bad. So that's why I wanted to clarify that this somewhat, yeah, I mean, if you've not played with these things, like this inequality is not in the same TV distance sense. This is in terms of majorization sense. So yeah, so that's why it's easily possible that you have some distributions which are in between, like two other distributions which are well behaved, but which are close, but yeah, the in between distribution, yeah, it's very bad. Any questions? Does this? Okay, good. So let's continue. So like as I was saying, like, why was this crucial? Like, I mean, I just wanted to illustrate. So going back, what was the theorem that we are trying to now prove? The theorem we are trying to prove is that for any strongly monotone problem, as long as you have roughly like n over epsilon squared samples, then you can learn the optimal policy. And the approach you're taking is you're going to learn each individual distribution separately just by taking the empirical distribution. I'm going to construct the product empirical distribution out of it, send it to my offline stochastic optimization oracle. Whatever algorithm it suggests, that's what I'm going to learn. The way we are going to prove its performance, it performs well, is the following. We're going to show existence of an upper and lower envelopes on your original distribution D, such that the true distribution D lies between this plus and D minus. Even the learned distribution lies between D plus and D minus. Although like the learned distribution, its TV distance is going to be very far off from D minus and D plus, because D plus and D minus have small TV distance to D. And in some sense, it's impossible for you to learn D hat, which is close to small, like to D in TV distance. So D hat is actually going to be very far from D plus and D minus in the TV distance sense. But in the majorization sense, it's going to be in between the two. And so that will basically suffice. Okay, so let's now try to complete the proof. So the exercise. So I'm going to prove again like slightly weaker result. Instead of n over epsilon squared, I'm going to prove n squared over epsilon squared. This n versus n squared is again the same annoyance that we'll be going via. I'm just going to apply like subadditivity of TV distance rather than applying like something like Hellinger distance and going via that. So that loses an extra factor, and you can shave that off by being a little more careful. Good. So now comes the question about how do I define these envelopes? So remember, like the proof steps are, I want to come up with, I have my original distribution. I want to come up with a slightly upper envelope and a lower envelope, such that my true distribution is in between the upper and lower envelopes, and also my learned distribution is between these upper and lower envelopes. And how am I going to define it is somewhat natural, like basically look at your distribution, the true distribution. The upper envelope is I'm just going to move the CDF by an additive epsilon prime. So at every point t, I'm just going to add it up like by an epsilon prime. Epsilon prime will be chosen to be like epsilon over n. So by additive, basically I'm just going to move every CDF slightly up. And clearly this will satisfy majorization because I've just literally moved every CDF up. Sorry, moving it. Yeah. So, and similarly on the other side, you'll just like move it down. So one thing, the two things to notice here is one is that it satisfies the majorization properties. And the other thing is that the TV distance is also small. Is this making sense? Oh, good, yeah. Yeah, so is this making sense? Like, let's look at like the first one. Like, so the reason here, what I've done is I've increased the CDF. So in particular, let's say like I look at t equals 0, like the minimum possible value. Originally, maybe my distribution had like almost zero chance of showing a value less than equal to 0. But now in other words, like what I've done is I've put epsilon prime, like a point mass distribution at 0, at support 0. In that sense, I've moved my distribution low. So that's why this is like a lower envelope and this is the upper envelope. In the upper envelope, I'm going to put like some epsilon prime mass at 0.1, like the maximum possible point in your support. And the reason this has TV distance at most epsilon is again, like you can define like a simple coupling between the two where you look at xi minus is nothing but xi, the original, times an indicator that the random variable is in that, as long as it's in the like bottom 1 minus epsilon prime quantile, like, or not in the top epsilon prime quantile. So by defining a simple coupling, you can argue that the TV distance is also within epsilon prime. Yes.
5 plus t is not a CDF. Like t is 1,
Yeah.
then it will not be 1, right?
You are saying, have I messed up something?
I'm just asking, fi plus t is, it's not a CDF, right? Like if t is one, then it will not be equal to one.
I might have made a typo here. But yeah, morally, what I want to basically say is like for the plus, I want to, oh no, I think, yeah, what you're saying is, okay, I think this is correct. Only t equals 1 is an exception because I have literally put a point mass of epsilon prime at 1. So this is true as long as t is strictly less than 1. For fi plus of 1, it will be exactly 1 as you're saying. Yeah, so this is correct. Just that I agree, like it should have been written like for t strictly less than 1 because I put in a point mass distribution at 1. Yeah.
The whole of the distribution on the same is higher and like lower envelope are like very like have a relation with the from the distance, for example, TV distance, right?
From the true distribution. Yes. Yes. Yeah. So that's the interesting thing. So like again, like this upper and lower envelopes, they are pretty much the original distribution, except up to like this moving like something putting slide mass at 0 or 1. That's why like it's impossible for you to learn these upper and lower envelopes as well because they're pretty much the original distribution. They have small TV distance to the original distribution and they're pretty much the original distribution. The funny part is that although you can't learn these upper and lower envelopes, you can argue that your learned distribution, because of the DKW inequality, is going to be also inside this upper and lower envelope. Because your DKW inequality ensured that for every point, your CDF that you've learned is up to like some epsilon, additive epsilon. So by applying, so like the second observation is there, whatever we have learned d hat is going to be also within these upper and lower envelopes because of the DKW inequality, as long as t is like 1 over epsilon prime squared times log 1 over delta, and epsilon prime is epsilon over n. This is the reason you'll get like n square over epsilon squared here. And as I was saying, like, yeah, the reason I've made epsilon to be epsilon over n is because I'm going to apply like sum over the TV distances for each I. So it will be, yeah, n times epsilon prime will be my final error. Yeah, this sum is, as I'm saying, like is a slightly loose. You can do slightly better bounds. We have something called Hellinger distance. Does this make sense? And yeah, so the main point of this envelopes are that there exists some upper and lower envelopes that contain the true distribution and also the learned distribution. And these envelopes have like their width is very small, like it's only like epsilon to epsilon. And once you have this, then basically the claim is that whatever is your learned distribution, so remember d hat is your learned distribution. I feed it to my oracle, optimization oracle, it returns me some opt hat. So opt hat is kind of the optimum solution, let's say, for d hat. So I'm evaluating the performance of opt hat on D, because whatever is my learned algorithm, I'm going to evaluate it on the true distribution, not on the learned distribution. That's what I care about. The claim is this is going to be at least the true opt of D on D, minus this epsilon and minus another epsilon. So minus 2 epsilon. So is the statement clear? Oh, actually, I'm running a bit. Yeah, okay. So let me just, the proof is again like just 3-4 lines. I realize yeah. So, I mean, although it's like just 3-4 lines, all you have to use somewhere is the strong monotonicity property. Digesting it will take like, I guess, a few 5 minutes. So I'll maybe just quickly gloss over it and the slides and everything is available to you. But the proof is literally just like, okay, the algorithm is basically opt hat. So the first is an equality. You replace D by D plus, and this is up to a TV distance, fine. Replace this D plus with D hat. This is using strong monotonicity. And like, so like at 2 places you have to apply this monotonicity. And weak monotonicity is only weaker as we know from strong. And then basically, yeah, it's just some rearrangement. So nothing fancy beyond that. It's more like the setup and so on that such a result exists. Okay, so what are the main takeaways from this part of the talk? Is that, so the main result that we saw or nearly saw is that roughly n over epsilon squared samples suffice to learn epsilon optimal policies for any strongly monotone problem. So this, as I was saying, includes our revenue maximization problems, our optimal stopping problems, our Pandora's box problems, and many others, which we did not talk about as well. Like, yeah, so this is like a very general result. Uh, so the high level idea is that, yeah, that basically you construct these envelopes to like in some sense think of like upper and lower envelopes in this blue band, and argue that whatever you've learned is also within this band, and try to prove from there. This result in general is tight, like this n over epsilon squared. You can show there are problems for which you cannot do actually better. For specific problems, one can do better. For instance, like the optimal stopping problem, we had a paper last year at NeurIPS, which showed that you can actually even remove off this n entirely. So this the so-called profit inequality or the optimal stopping problem, you can actually remove the dependency on n entirely. I mean, okay, it appears in the log, I guess, O tilde. So there's a log n there, but besides that, there's almost no dependency on n. So for specific problems, you can hope to improve this. Yeah, in this summer school, I'm mostly focusing on just, at least today, on just general results rather than problem-specific guarantees. So for some problems, you can do better, but yeah. Okay, I think, yeah, let's take maybe a break, and I'm happy to take questions.